Hi guys, welcome to our MPLAB XC8 tutorials for Absolute Beginner series. This is tutorial 36, the I2C communication with PIC microcontroller. The I2C was created by Philips Semiconductors for use in communication of peripheral devices within a TV set and commonly written as I2C. The I2C stands for integrated circuit and allows communications of data between I2C devices over two wires. The I2C is sometimes called two-wire interface. As you can see from this figure, we can have many devices connected to a PIC microcontroller using only two wires and two pins of the PIC microcontroller. The I2C has become one of the most common serial communication protocols in electronics. The devices don't have to be identical as long as they support I2C protocol. In this illustration, you can see we've got three different devices. We've got one temperature sensor, we've got one real-time clock, and we've got one LCD. They are all connected to one PIC microcontroller using two lines, because they all support the I2C protocol. We could also add some more devices. Communication takes place from the master, in this example is going to be our PIC microcontroller, to the selected slave device. In this illustration, the master sends data to slave 2 only and the rest will be ignored. Both the SCL and the SDA lines are open drain drivers. So this basically means that the chip can drive its output low, but it cannot drive it high. For the line to be able to go high, you must provide pull-up resistor to 5 volt, one resistor from the SLC line to 5 volt, and the other one from SDA line to 5 volt. You only need one set of pull-up resistor for the whole line. So even if you've got 10 devices or 3 devices or 1 device, you only gonna need these 2 resistors. The value of these resistors is not really critical. Anything from 1.8K to 47K can be used. So their values depend on the length of the bus. If these resistors are missing, then the SEL and the SDA line will always gonna be nearly 0 volt and the I2 bus will not work. The I2 bus is suitable when the microcontroller and the device which the microcontroller should exchange data with are in close proximity, like on the same PC board. These devices can be memory modules like the 24AA serial EEPROM. They can also be temperature sensors like the TC74. They could be real-time clocks like the popular DS3707. They could also be digital to analog converters, analog to digital converters, input-output expanders, and so on. So these devices, they can basically be anything. You can even connect to a PIC microcontroller as well. We've got only 2 pins of the PIC microcontroller that we're gonna use. The first one is SDA, which is serial data, and the other one is serial clock. This communication can support a maximum of 112 devices, so you can basically have 112 devices on this bus line. The specification declares that 128 devices can be connected to the I2C bus, but it also defines that 16 are reserved addresses, so you cannot use those 16 addresses. So as this is a serial communication, like the SPI and the USART, among others, each serial communication, it's got its own advantages and disadvantages. So you can compare and see which one is going to work best for your application. These are some of the few advantages of using the I2C bus. The first advantage is faster than asynchronous serial, allowing large quantities of data to be transferred quickly. But this communication is slower than SPI. In I2C, the bus can operate at various speeds, which are generally dictated by the slowest device on the bus. So if you've got the slowest device on the bus, it's gonna pull down the speed of the rest of the devices. The common bus speeds are 100 kilobits per second in standard mode. You could also have 400 kilobit in fast mode and 1 megabit in high speed mode. But a new revision of the specification allows for a maximum throughput of 3.4 megabit in high speed mode. Another advantage of using I2C over SPI, as we're gonna learn the SPI tutorial, is the number of pin used. Connecting a single master to a single slave with SPI bus require a minimum of 4 lines. Each additional slave is gonna require 1 additional chip select input-output pin on the master. So this can become very cumbersome in situations where lots of devices must be slaved to one master. With I2C, we don't have that problem because I2C requires only 2 lines, the data line and the clock line. Whether we've got one device or many devices on the lines, we're only gonna need 2 lines. Another advantage of using I2C, unlike the SPI bus, I2C can support multi-master system, allowing more than one master to communicate with all the devices on the bus. Although the master devices can talk to each other over the same bus and must take turns using the bus line. I2C support multiple slaves, up to 112 slave devices. I2C devices may have external addresses pins which allows you to assign a unique address to each device, and therefore it allows multiple of the same devices to operate on the same bus. And the other advantage that we can note is the I2C supports slave acknowledgement, which means that you can be absolute sure that you are actually communicating with something. Whenever you send something to the slave, then the master is going to receive an acknowledgement, unlike the SPI, where a master can be sending data to nothing at all and there's no way to finding out. As with other communications, nothing is perfect. Each communication has got its own advantages and disadvantages. So here are some few disadvantages of using the I2C. The first one is communication via I2C is more complex than with USART or SPI. The signaling must adhere to a certain protocol for the devices on the bus to recognize it is a valid I2C communication. The I2C draws more power than other serial communication buses due to open drain topology of the communication line. Since devices can set their communication speed, slower operational devices can delay the operation of faster devices. The other problem that you can encounter when using an I2C, as this is a shared nature, the I2C bus can result in the entire bus hanging when a single device on the bus stops operating. Cycling the power to the bus can be used to restart the bus and restore proper operation. And lastly, the I2C is designed for fairly short range. This basically means that devices which are on the same PC board as the master or via a relatively short cable compared to the RS-232, RS-485 and the CAN bus. This diagram shows the I2C bus operation. As this is a synchronous serial communication, a clock signal is necessary to synchronize the operation of both devices. It's always generated by the master device and its frequency directly affects the baud rate. When the master and the slave component are synchronized by the clock, every data exchange is always initiated by the master. So when you enable the MSSP module, which is Master Synchronous Serial Peripheral, it waits for the start condition to occur. The master device first sends the start bit, which is going to be logical 0. Then it's going to send the 7, if you are using 7 address baud or 10 bit address of the selected device. And finally the bit which requires data. If it sends a 1, then the master is requesting data. It's basically the master is reading from the slave. And if it sends a 0, then the master is sending data to the slave. So at this point, if the slave address which was sent exists on the bus, then the slave will send an acknowledgement bit to the master. Data is then transferred on the serial data line in the direction that was specified by the master. An acknowledgement bit is sent at the end of each transferred byte but the receiving end of the transmission. The only exception is that when the master is in receive mode and the slave in transmit mode, the master will not send an acknowledgement bit after the very last bit received. And lastly, the communication is stopped with the master sending a stop command. The start and the stop command are simply a transition from high to low on the SDA line with SCL high if you are sending a start command, or from low to high on the SDA line with SCL high if you are sending a stop command. So this is a simple demonstration how you can connect a PIC microcontroller as a master to a slave device. In this example, we are using the DS1307 real-time clock as a slave in this I2C bus. The first thing we're gonna connect the SCL, which is a serial clock pin of the master. In this case, it's gonna be on pin RC3. Is connected to the SCL of the slave device, and the SDA, which is a serial data of the master, is connected to the SDA of the slave device. And here we've got two pull-up resistors, 4.7 each. Basically, this is how you can connect your slave device. If we had other slave devices, we could also connect them on the same bus line. This is gonna be the end of this part 1. In part 2, we're gonna learn how to configure the I2C bus with MPLAB Code Configurator. Thank you guys for watching this tutorial, and don't forget to subscribe to this YouTube channel to receive more tutorials in the future. And if you have a question, please feel free to leave a comment on this video. And I'll see you guys in part 2. Thank you.